All right, y'all. Today we're going to be talking about graphing exponential functions. So we've talked about exponent properties, we talked about log properties and how we can use them to simplify and solve equations. And now we're going to put a few of those skills to use as we talk about actually graphing these types of functions. So our first one we're going to look into is we're going to look into exponential functions. So the function f of x is equal to a times b to the x is an exponential function with base b, where b is some positive real number other than 1, and x is any real number. And we call it an exponential function because the x, the independent variable, is actually in the exponent. So that's where it gets that exponent part of its name. And to help us graph today, we're going to make a little bit of an x by y table. Okay, and let's just do a couple of easy points. So -2, -1, 0, 1, and 2 to make it pretty straightforward for us. So plugging in -2, that would be 2 to the -2, which would be 1/4. Plugging in -1, 2 to the -1st, which would be 1/2. 2 to the 0, like anything to the 0 power would be 1. 2 to the first would be 2. And 2 to the second would be 4. So just a reminder, those negative exponents are fractions because any negative exponent by our rule means I send it down to the bottom of the fraction. Okay? I take the reciprocal. So let's go ahead and add our points in. So -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. And we can start to see those points take shape. As we go in the negative direction, they start to get smaller and smaller. If I kept going up 2 to the -3rd, 2 to the -4th, it would be a smaller and smaller fraction. And vice versa in the other direction, as my x's get larger and more positive, I'm growing exponentially. 2, then 4, my next one would be 8, and then 16. And so it creates this nice little exponential shape from the left to the right. Okay. Now, the only other thing that we haven't really talked about is if we notice to the left, it's getting smaller and smaller, but is it ever actually going to reach 0? Well, if I keep taking 2 to some power, negative power, so 2 to the -3rd, 2 to the -4th, that'd be 1/8, and then 1/16. Even though it would keep becoming a smaller and smaller fraction, it wouldn't actually ever become 0 because I can't multiply by a base of 2 and make it into nothing. If I just keep multiplying by 2s, it's still just going to keep getting smaller and smaller, but never actually becoming 0. So our exponential functions actually have an asymptote. And that asymptote for our parent function does occur right here at the x-axis, okay, because it is an asymptote of 0, and we would of course write that as it goes right through the y-axis at 0 as y is equal to 0. Okay, let's talk through some of these other key features as well while we're down here. So our domain, I can plug in negative values to my exponent, I can plug in positive values to my exponent. We didn't plug any in, but I could even plug in fractions if I wanted to, or decimals into my exponent. So it doesn't seem like there's any x values that I can't plug in. So my domain in this case would be all real numbers. Now for our range, we definitely have all those positive values, but we are framed by that asymptote. Notice our exponential function is never going below that value of 0. So we would say our range is y is greater than 0. For our y-intercept, we can see that we do cross the y-axis right there at 1. So our y-intercept, we want to make sure we still write it as a point, so 0, 1. And then increasing or decreasing, remember that has to do with the y values. If they go up or down as we read our graph left to right, just like a book, our y values do go up from left to right, so we would say this function is increasing. And that is our exponential parent function in a nutshell, y'all. Pretty straightforward. Okay. The other thing we're going to talk about today is we're going to be adding in transformations to our exponential functions. And we have 3 transformation variables we're really going to key in on, and that is A, C, and D. And our a value, it's multiplied in the front. It's going to cause reflections across the x-axis with our exponential function, as well as any vertical stretches or compressions if it's a value greater than 1 or a value between 0 and 1. Then our c value is going to be our horizontal shifts, our shifts from the left to the right. One thing to keep in mind with our c value, because it's inside those parentheses, it's always the opposite of what it is in the parentheses. And then last but not least, our d value is going to be our vertical up and down shifts, as well as that equation of the asymptote. So we didn't talk about it in our parent function, but our d value here is technically 0, which is why our asymptote is y is equal to 0. So that d is going to both shift us up and down as well as shift the asymptote. So let's look at a real quick, and we're going to start talking through some of these transformations. So for a, we have f of x is equal to negative 3 to the x minus 4. So the first thing I want to do is I want to start identifying some of the transformations that I'm going to see. So I have this negative in front. So that negative means I am going to reflect across the x-axis. That's my a value. Then other piece that I have is I do have this negative 4, which means I am going to be shifting down by 4, as well as my asymptote is going to shift down to y is equal to negative 4. So your d value does double duty with our exponentials. It's going to shift up or down as well as changing that asymptote. So we're going to go ahead and add that asymptote on here at negative 4. And then for actually graphing our function, I did 5 points for our parent function, but we actually only need 2 points to get a good idea of the shape of the exponential function. And we're going to choose values that are really easy to evaluate for us, stuff that we can really do in our head without a calculator. Because if I had a calculator, I could just graph this exponential function in my graphing calculator, but we don't have a calculator, so we need to pick values that are easy for us to plug in. And the easiest exponents to evaluate are an exponent of 0 and an exponent of 1, because anything I take to the power of 0 is going to be 1, and anything I take to the power of 1 is just going to be that base. So plugging in, I get negative 3 to the 0 minus 4, which is equal to negative 1 minus 4, which is equal to negative 5. Okay. Doing the exact same thing for 1, I would get negative 3. We're raising it to the power of 1 minus 4. That would be equal to negative 3 minus 4, which is equal to negative 7. So that gives me my 2 points, 0 comma negative 5 and 1 comma negative 7. I can go ahead and add those 2 points onto my graph. So x is 0, negative 5, x is 1, y is negative 7. So now I can see that shape. I'm going to start close to my asymptote and then do that exponential shoot up through my points. And let's compare parent function to our transformation function. So does it look like we reflected across the x-axis, which really for exponential functions, your x-axis is like your asymptote. So does it look like we reflected across our asymptote? Yes. And then does it look like we shifted down 4? We definitely did shift down 4. So that's going to be how our exponential functions really flesh out. Finding those 2 points, identifying those transformations, and really shifting the asymptote. The asymptote is going to kind of be your grounding piece that's going to show you where to go. So the last thing we want to add in is our key features, which were domain, range, our intercept, and then of course if it was increasing or decreasing. So our domain, still all real numbers. I can still plug in any value for x, and our domain for exponential functions is actually always going to be all real numbers. It's never going to change. Our range though, because we shifted down, is going to be a little different. It is now less than negative 4. So your range is always going to be affected by 2 things, a shift up or down, as well as any reflection is going to switch that an equality sign if it's going to be less than or greater than whatever the value of the asymptote is. Okay. Then for our y-intercept, we are now crossing the y-axis at -5. So 0, -5. And then increasing, decreasing because of that reflection, this function is now decreasing. Pretty straightforward. Okay. So that's A. Let's do one more together, see if we can keep up with all of our stuff. So on B, we have f of x is equal to 4 to the x plus 2. In this case, we actually only have one transformation. It's that plus 2, which means it's the c value. Remember, it's always opposite of what's in the parentheses. So we are actually going to shift to the left by 2. And then we don't have it written, but our asymptote, because we don't have a d value, that means our asymptote is going to be at our standard asymptote of y is equal to 0. Okay, so I'm going to go ahead and add my asymptote on first. I always believe it helps to kind of frame our function where we need to be. Okay, we're not going to have a reflection across the x-axis, so we should be above the asymptote with our points. And then just like last time, we want to plug in points that's going to give us an exponent of 0 and 1. But a little different this time is we don't just have x in the exponent. Now we have x plus 2. So for our x values, I'm actually going to shift those values we plug in by that 2 so that I still have an exponent of 0 and an exponent of 1. So I'm going to plug in -2 and -1. So plugging in -2 and -1 to our function is still going to give us an exponent of 0 and an exponent of 1 when we're evaluating it out. So 4 to the -2 plus 2 would be equal to 4 to the 0, which would be equal to 1. So that's our first point. And then 4 to the -2, not -2, we just did -2, to the -1 plus 2 would be equal to 4 to the 1st, which is equal to 4. So we have 2 points. We have -2, 1, and we have -1, 1. So -2, 1, sorry, -1, 4. So -2, 1, and then -1, 4. And now we can see that exponential growth, which we should have because we're not reflecting across the x-axis. So we're going to stay really close to our asymptote and then shoot up through our points like so. Of course, we want to make sure we come back and add that arrow onto the left side. So this one, the only transformations we had is we shifted to the left by 2, which we can definitely see that we've shifted off the y-axis just a bit. So let's add in our key features real quick before I let you practice them on your own. So our domain is all real numbers still. That never changes. Our range this time, because we didn't shift up or down or reflect, it's just going to be that standard parent function range of y is greater than 0. Our y-intercept, so if you notice, because we shifted off, we didn't actually get that y-intercept. But the y-intercept always comes from plugging in 0 for x, because that's what the x value of any y-intercept is. So if I plug 0 in for x, I would get 4 to the 0 plus 2, which is 4 squared, and 4 squared would be 16. So my y-intercept, if I was to graph a little bit further, would be 0, 16. And then last but not least, is this function increasing or decreasing? And I would definitely say it is exponentially increasing as we read left to right. So this one is increasing. All right, y'all, I want you to go ahead and try C and D on your own. So do the same process. Identify your transformations, set up your table, plug in those 2 points so that you're getting an exponent of 0 and an exponent of 1, and then graph your asymptote, graph those 2 points, and then draw that smooth exponential curve, hugging the asymptote and going through those 2 points. So go ahead and pause the video now so you can practice. All right, y'all, so just to finish up our talks for today, and we're going to shift this a little bit so we can actually read everything. Okay, so looking at C and D, let's start with C. So C, we have f of x is equal to 1/2 to the x plus 2. The only transformation we actually have occurring here is that plus 2. We are shifting up by 2. Now, we didn't talk about this that much, but the base is actually really important in exponential functions because the base is telling us what we're multiplying each value by as we raise it to certain exponents. So if our base is a whole number like 2, 3, 4, 5, then it should be getting bigger as we raise it to higher exponents. If our base is a fraction like 1/2, then as we keep multiplying, it's actually going to get smaller. And we see that play out in this function because when we take it to the 0 power, 1/2 to the 0 is 1. 1 plus 2 is 3. So that gives us our y-intercept of 3. But then when we take it to the first, 1/2 to the first is 1/2. 1/2 plus 2 is 2.5. So we're now actually getting smaller. And if I kept multiplying by more 1/2, so 1/2 to the second would be 1/4, because it'd be 1/2 times 1/2, which is 1/4. 1/4 plus 2 would be 2.25, so a little smaller again. So as I keep multiplying by 1/2, I actually get smaller instead of bigger. We call this exponential decay instead of exponential growth. So even though we didn't have that reflection, this function is actually still going to be decreasing. But we can see that the shift up of 2 is reflected in the asymptote at y is equal to 2. Our domain is still all real numbers. Our range is now y is greater than 2 because of that shift up by 2. Our y-intercept is 0, 3. We can see that by plugging in 0 for x. And then increasing or decreasing, like we said, this one is exponential decay, so it's definitely decreasing as we go left to right. Last but not least, y'all, let's talk about D. F of x is equal to 2 times 2 to the x plus 1. So once again, we had that C shift, so we're going to shift to the left by 1. And then this time we have a value greater than 1 for A, so we're actually going to be vertically stretching it by 2. So we're multiplying by that 2 each time for our points. So plugging in, I started with -1 instead of 0 because -1 plus 1 is going to give me that exponent of 0. So plugging in -1, -1 plus 1 is 0. 2 raised to the power of 0 is 1. 1 times 2 is 2. So that gives me my first y value. Then plugging in 0 because 0 plus 1 gives me that exponent of 1 that I want. So 0 plus 1 is 1. 2 to the first is 2. 2 times 2 is 4. So we get the 2 points of -1, 2, and 0, 4. And we can see in our graph that does stretch it out just a little bit. It looks like it grows a little faster than normal. Our domain is still all real numbers. Our range is still y is greater than 0 because our asymptote didn't shift up or down. Our y-intercept this time is 0, 4. And then increasing or decreasing, this one is definitely going to be increasing as we go left to right, y'all. Okay, that pretty much wraps up graphing exponential functions, y'all. So the big thing to remember is to identify those transformations, being able to tell me what's going to happen to the graph, and then being able to plug in those correct points. So if the exponent is just x, you're going to be plugging in 0 and 1. It's going to be really straightforward. If the exponent has anything else extra in it, it has a plus or it has a minus, you're going to have to adjust a bit what you plug in so that you still get that exponent of 0 or 1. All right, thanks, y'all.